Earth has a pollution problem, and it comes in more than one form. On one end of the spectrum, there are the everyday pollutants most of us are familiar with. Plastics choking waterways, overflowing landfills, the mountains of household waste generated by billions of people going about their daily lives. On the other end, there are far more dangerous and complex threats, the kind that don't just make a neighborhood look unpleasant, but can render entire regions uninhabitable. Industrial waste in its most extreme forms, including nuclear byproducts, biohazardous materials, and concentrated chemical toxins, poses a profound and ongoing challenge to human civilization. These substances seep into soil and groundwater, stifle entire ecosystems, and disproportionately affect the health of vulnerable communities around the world, communities that often had little say in where these materials were produced or stored in the first place. Of all these waste categories, nuclear material is arguably the most vexing. It isn't just dangerous in the way a sharp object or a toxic chemical is dangerous. It remains lethally radioactive, across timescales that dwarf recorded human history. The half-lives of certain nuclear isotopes stretch into the tens of thousands of years, meaning that waste generated today will still be capable of causing radiation sickness and environmental contamination long after every living person on the planet and countless generations of their descendants are gone. So far, the best solution our civilization has been able to devise for dealing with this material is to dig very deep holes and bury it, sealing it away in geological repositories, and hoping the surrounding rock stays stable for millennia. It works, more or less, but it's hard to feel entirely comfortable with an approach that essentially amounts to hoping for the best across an almost incomprehensible stretch of time. Which raises an obvious and admittedly tempting question. If the problem with nuclear waste is that it sticks around on Earth for so long, why not simply remove it from the equation entirely? Why not load it onto a rocket, aim that rocket at the sun, and let 93 million miles of nuclear fusion take care of what we started? The sun, after all, is essentially a colossal ongoing thermonuclear reaction. Surely a few barrels of radioactive waste would be trivial by comparison, incinerated and absorbed without a second thought. It sounds like the ultimate solution, a clean, permanent, cosmic disposal method. So what's stopping us? Before we start, I want to tell you something. A lot of strange things have been happening in space lately, so subscribe to this channel right now, and I'll tell you even more secrets of space. And write in the comments below what you think about all of this. To begin answering our question, it's actually really hard to crash anything into the sun, and the reasons why are far more counterintuitive than most people expect. Let's take a closer look at what's really going on. Suppose we've gathered together a massive pile of toxic waste destined for the sun. Maybe it's radioactive material, chemical sludge, or whatever else humanity has managed to produce in industrial quantities that we'd rather never think about again. The first thing we'd need to figure out is how to get it into space. Easy, right? We've been launching stuff into space for the better part of a century, ever since the first satellites went up in the late 1950s. To get our trash pack through the atmosphere and out past Earth's orbit, we'd need to accelerate it to a velocity of 11.2 kilometers per second. This is the speed known as escape velocity, the critical threshold at which the kinetic energy of the payload surpasses Earth's gravitational potential energy, allowing it to break free without any further thrust. It's the speed at which you stop falling back down and start flying away for good. Once free of Earth's orbit, our garbage craft is on course for solar collision, right? Wrong. Once our package escapes Earth's orbit, it isn't floating freely in empty space, just waiting to drift into the sun. It's still gravitationally bound to the sun, inherited a healthy orbit around it the moment it left our planet, and will continue circling that orbit indefinitely unless something changes. Put super simply, Earth and everything on it is moving sideways relative to the sun at about 30 kilometers per second. That's roughly 108,000 kilometers per hour, a speed that most people never stop to fully appreciate. Combining this sideways motion with the gravitational pull of the sun is what keeps us locked in a stable orbit. Gravity pulls us inward, but our sideways velocity keeps carrying us forward, so instead of spiraling in or flying away, we trace an elegant ellipse around our star, year after year. If the sun were to somehow lose its gravitational pull, we'd fly right past it at 30 kilometers per second and keep going, sailing off into the outer solar system and eventually into interstellar space. Conversely, if we on Earth were to lose our sideways motion entirely, we'd have nothing counteracting solar gravity, and we'd fall straight into the sun in a matter of weeks. So there's hope for our garbage ball yet. How could we lose our sideways motion to make this solar freefall happen? Well, there are two broad approaches, and both of them are genuinely difficult in their own fascinating ways. The first option is to bring up enough fuel to brake in space. Now, technically speaking, you can't really brake in the vacuum of space the way you tap the pedal in a car, because there's nothing to push against and no friction to slow you down. But the next best thing would be to configure our garbage payload's propulsion system to generate thrust in the direction opposite to its sideways motion. By firing engines backward relative to the direction of travel, you cancel out that lateral velocity, slowing the craft down and letting the sun's gravity do the rest of the work, pulling the payload on a long inward arc until it finally plunges into the solar surface. Earth orbits the sun at 30 kilometers per second, so to fully break a garbage rocket launched from Earth, you'd need to be able to accelerate it by 30 kilometers per second in the opposite direction of its movement. That is an enormous amount of delta V, which is the technical term for the change in velocity a spacecraft can achieve. Generating that kind of thrust requires a staggering quantity of propellant, far more than the payload itself would likely weigh, making the whole endeavor almost absurdly expensive and logistically nightmarish. Here's where it gets genuinely weird though, and this is one of those beautiful moments where orbital mechanics defies common sense. The closer you are to the sun, the harder it is to crash into it. Let me explain. The closer you are to the sun, the faster your orbital velocity has to be to maintain a stable orbit at that distance. Mercury, nestled close to the sun in the inner solar system, orbits at a dizzying 48 kilometers per second, while distant Pluto, far out in the frozen reaches of the outer solar system, cruises along at a comparatively leisurely 4.7 kilometers per second. The faster your orbital velocity, the more you need to decelerate in order to eliminate that sideways motion and enter a free-fall trajectory toward the sun. So Mercury actually needs to shed far more speed than Pluto does to achieve the same result. That's why, as counterintuitive as it sounds, it is actually much more fuel efficient to fly outward to the outer solar system first, slow down gradually there where your orbital velocity is already much lower, and then free fall all the way into the sun from that tremendous distance. You spend less fuel fighting orbital mechanics, and gravity does more of the heavy lifting over the long inward plunge. It's not inconceivable to accelerate a spacecraft to 30 kilometers per second. NASA's Parker Solar Probe, for instance, accelerated beyond 176 kilometers per second, making it the fastest man-made spacecraft ever built, and a remarkable testament to what modern propulsion engineering can achieve when conditions are right. The probe harnessed the immense gravitational pull of the sun itself to reach those extraordinary speeds, which is precisely what makes that achievement so instructive and, in a way, so frustrating when you consider the problem from the opposite direction. But this brings us back to the problem of fuel. To make this break and fall method work, you'd first have to launch your garbage payload into orbit around Earth, then separately launch all the fuel required for the journey to the sun into orbit as well. Once both pieces are in orbit around Earth, you'd rendezvous the two, fuel up your payload, and then fire the engines to accelerate it past Earth's orbital velocity and out into a wider orbit around the sun. At that point, the spacecraft would be coasting on a trajectory that keeps it bound to the solar system, not plunging toward the sun. That's the critical issue. Simply escaping Earth isn't enough. You then have to burn through whatever remaining fuel you have left to decelerate the spacecraft dramatically, stripping away enough velocity that it loses its stable solar orbit and begins to free fall directly into the sun. You might wonder why you couldn't just launch the payload and the fuel together at the same time and simplify the whole operation. The answer is brutally straightforward. It's simply too much fuel. The numbers become almost incomprehensible when you start working through them. For context, the Saturn V rocket, the most powerful launch vehicle ever successfully flown, and the machine that carried human beings to the moon, required approximately 2 million liters of fuel just to push its payload beyond Earth's gravitational grip at the escape velocity of 11.2 kilometers per second. A mission designed to haul waste material all the way to the sun and then actively decelerate it into a collision course would require orders of magnitude more fuel than that. Not a little more, orders of magnitude more. No rocket technology that exists today would even come close to being capable of carrying the sheer volume of propellant that a journey like this demands. The rocket itself, fueled up for the mission, would be so overwhelmingly massive that getting it off the ground in the first place becomes its own impossible problem. So scenario 1 is firmly off the table. What other options are there? Another way to decelerate a spacecraft in space is through a technique called a gravity assist. Usually, when people talk about gravity assists, the image that comes to mind is the kind that flings a probe outward with tremendous speed, like the celebrated maneuvers that sent the Voyager spacecraft arcing through the outer solar system and eventually beyond the boundary of our solar neighborhood entirely. But gravity assists are not exclusively about gaining speed. They can work in reverse, bleeding velocity away from a spacecraft rather than adding to it. The mechanics work like this. If you approach a planet from behind, swing in front of it, and then exit on the far side of the planet relative to your original path, your spacecraft effectively transfers some of its energy to the planet. The planet, being unimaginably more massive, barely registers the exchange. but the spacecraft loses a measurable and useful amount of velocity in the process. It's an elegant trick that uses nothing more than gravity and geometry to reshape a trajectory without burning a single drop of additional fuel. This technique has already been used successfully on real missions heading to the inner solar system. Both the Messenger probe and the more recent Bepi-Colombo mission have employed gravity assists specifically to shed velocity and work their way into orbit around Mercury, the innermost and smallest planet. Getting to Mercury is notoriously difficult precisely because you're falling toward the sun the entire time and constantly picking up speed you don't want. The catch, though, is time. Bepi-Colombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, launched in 2018 and will only arrive into its final orbit around Mercury in 2025, nearly 7 years after leaving Earth. What's striking is that the total distance it travels along its winding, looping trajectory is actually greater than the straight-line distance between Earth and Pluto. That extraordinary detour exists for one reason: a single gravity assist simply doesn't remove enough velocity to do the job. Bepi-Colombo requires 9 separate gravity assists across multiple planetary flybys to shed enough speed to be captured by Mercury's gravity. 9. Each one a carefully calculated orbital encounter, each one shaving off a little more velocity, nudging the spacecraft incrementally closer to the slow, controlled approach it needs. Similarly, crashing our garbage into the sun is entirely a game of carefully calculated orbital mechanics, and the math is far less forgiving than it might seem. If we don't slow down enough, our waste-laden spacecraft will simply settle into a stable orbit around the sun, rather than plunging into it, endlessly circling without ever reaching its destination. If we slow down too abruptly or at the wrong point in our trajectory, we risk getting captured into some other unintended orbit, one that could take years or even decades to correct. The precision required is extraordinary, and any miscalculation doesn't just mean a delayed arrival. It could mean the mission fails entirely. At this point, you might be thinking, this is all still feasible. It's hard, sure, but it's within the realm of possibility. So why don't we just do it? And that's a completely fair question. The short answer is possible, yes. Worth the time, effort, risk, and staggering technical challenges? Probably not. Let's think carefully about what could actually go wrong, because the list is longer and more sobering than you might expect. First of all, we're proposing packing a rocket full of nuclear waste, biohazards, and toxic plastics, and then igniting it on a launch pad here on Earth. A launch failure or mid-air explosion wouldn't just be a setback. It could be an environmental catastrophe of the highest order, scattering radioactive and biological material across a wide area in ways that could affect ecosystems and human health for generations. And launch failures are not as rare as we'd like to believe. Even the Soyuz rocket, widely considered the most reliable and battle-tested launch vehicle in history, with decades of successful missions behind it, still carries a failure rate of around 2 to 3%. That might sound small, but when the payload includes nuclear waste, a 1 in 40 chance of catastrophic failure is not a margin any responsible agency should be comfortable with. The consequences of getting it wrong aren't just expensive or embarrassing, they're potentially irreversible. Even if the launch goes perfectly, the mission itself would be so staggeringly expensive that no sane budget committee on Earth would approve it. Space launches already cost hundreds of millions of dollars for conventional payloads, and a mission requiring the kind of complex gravity assists and prolonged propulsion burn needed to decelerate into the sun would multiply those costs many times over. There are already far too many competing priorities in the space science world. Missions that could discover new worlds, advance our understanding of the universe, or develop technologies that genuinely benefit humanity, all of which would lose funding in favor of what is, at its core, an elaborate garbage disposal program. And here's perhaps the most ironic twist of all. If you really were determined to launch waste off our planet permanently, it would actually be easier, quicker, and cheaper, though still wildly expensive, to shoot it out of the solar system entirely, toward interstellar space. Counterintuitive as it sounds, escaping the sun's gravitational grip entirely requires less energy than fighting your way inward against it. To escape the solar system from Earth's orbital position, you need to reach a velocity of about 42.1 kilometers per second, which means you only need to accelerate by about 12.1 kilometers per second beyond Earth's existing orbital speed. Falling into the sun, by contrast, demands that you shed nearly all of that existing orbital velocity, which requires a much more dramatic and fuel-intensive change in momentum. So there you have it. We don't shoot garbage into the sun because it is super hard, super risky, and super expensive. 3 strikes that together make it one of the least practical ideas in the history of waste management. We're almost certainly better off redirecting that energy and ingenuity into being more conscious about what we consume in the first place, and investing seriously in how we recycle, reuse, and reduce the waste we generate here on the only planet we actually call home. That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.